My dear students, welcome to the discussion on some basic concepts and problems from electrostatics. We'll discuss today some basic aspects of Coulomb's law. As we all know that the subject of electrostatics revolves around charges which are at rest. So first thing we must be able to know or define what do you mean by an electric charge. That's a fundamental question. So an electric charge is actually the physical property of matter which causes it to experience a force when placed in an electromagnetic field. So this is a very important concept, and the SI unit of the charge is Coulomb. As our major target will be to understand and solve problems pertaining to a particular theory, we must be very careful about the choice of the units. So please pay your attention to the units of the various physical quantities that are used in the current discussion. Now, Coulomb's law is very common to all of us. We all know it, but still a very brief review about it. Coulomb's law actually gives an estimate about the force exerted between the two charges. In fact, there may be multiple charges also, but that we'll cover in the next video. We'll first discuss the basics and the applications of that. The force is proportional to the product of the two charges. The charges, they are having a distance between them. The force is also inversely acting depending on the square of the distance. And last but not the least, it acts along the line joining between the charges. So, if we consider that there are two charges, one charge is here, this charge is having a value q1. It may be a positive charge or a negative charge, and at a certain distance there is another charge q2, and the distance between them is r. We join them with a line and the distance between them is r. Then the force is actually proportional to q1 q2. The force is proportional to q1 q2 and inversely as the square of the distance, so inversely as r square. So q1 q2 by r square, and whenever this proportionality constant we remove it, we know a proportionality sign, we remove it, we get a constant of proportionality, and that constant we say call it k. So it is k into q1 q2 divided by r square. And in SI system, this k is denoted as 1 by 4 pi epsilon naught. So we have to remember it very carefully that we are working in the SI system, and this k is denoted as 1 by 4 pi epsilon naught. And this quantity epsilon naught is called as the permittivity of free space. This is called permittivity of free space. Now, we must be able to remember the values of these constants k and epsilon naught. So we have to keep them in our mind. In fact, in majority of the calculations, the value, we just write down the formula once again here. So F is k into q1 q2 divided by r square. This will be the very important working formula, and this we also write as 1 by 4 pi epsilon naught q1 q2 by r square. This will be our working formula, and the value of epsilon naught, please be careful about these values. Value of this epsilon naught will be 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square. So the value of epsilon naught, I am repeating, 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square. And the value of K, this value of K, which is 1 by 4 pi epsilon naught, you have to remember this value because this will be very, very helpful when we solve the problems. So 1 by 4 pi epsilon naught, of substituting this value, it comes out to be 9 into 10 to the power 9 Newton meter square per Coulomb square. So whatever we are working on these, we are considering, of course, the SI units. So that must be very, very carefully kept in mind that we are doing the SI units in the SI system of units. And most importantly, when we solve the problems, I've already done a video, you can refer to that in this channel, that whenever you solve a particular problem, you choose the units in a particular system. The data will be given, you choose them in a particular system. So this is about the scalar form. This format of Coulomb's law is in scalar form. Now if we consider in vector form, as we know that the force will be acting on both these charges. So in vector form, we must understand and be able to quantify in terms of vectors, and we must be able to write the expressions. So this one is Q1, so we can call this charge 1, and this one is Q2, and of course, as we know, the distance between them is R. The distance between them is R. Say consider that we have we have unlike charges. Say this one is a positive charge, and say this one is the negative charge. So the convention is we consider that a force is acting. So this is F12. This is F12, and from Q2 side, the same force will be acting. This force will be calling as F21. Of course, these forces will be considering them as vectors. These forces will be considering them as vectors. And say for example, we take this n cap in this positive x direction in the unit in the direction of the unit vector. Okay, in the direction of the unit vector. So that gives us an estimate that F12, if we consider this as the direction of the unit vector, so F12, this particular vector, that will be a positive, this force will be positive, and F21, this vector will be negative. So F12 will be positive and F21 will be negative. And of course, the expression remains the same. So if we want to write F12, which is the force on 2 due to the charge 1, so that will give us Q1 Q2 divided by 4 pi epsilon naught r square, that multiplied by n cap. And similarly, in a similar fashion, F21, that will be minus, because here it will be opposite to n cap, so minus sign, this minus gives the direction, so it will be Q1 Q2 divided by 4 pi epsilon naught r square into n cap. So one is equal and opposite that of the other. So this we have done, these two charges, they were unlike charges. This we have worked for unlike charges. We can similarly work out for like charges. So I leave it to all of you. You can work it out and find out whether you have understood it correctly. So I hope this basic understanding is clear now. So with this little bit of understanding, let us proceed to the next step. Let us take up a problem and try to solve it. So this problem states that there is a point charge q1, a value is given, and the distance is also given from another charge q2. So determine the attractive force on each charge. Why it is called attractive force? Because you can find out q1 is having a plus value and q2 is having a minus value. So plus and minus are there. So there will be, of course, they will be giving an attractive force. So as I told in my earlier video, so let us first note down the data that is given when we want to solve it. Let us follow the process. So Q1 is given as 3 into 10 to the power minus 6 Coulomb. Q2 is given as minus 1.4 into 10 to the power minus 6 Coulomb. And the distance r is given as 0.14 meter. And we know that for such problems we will be requiring the value of k. So we note down the value of k as we always do. So it is 9 into 10 to the power 9 and the unit is Newton meter square per Coulomb square. So we are now equipped and we know that from Coulomb's law, the force will be simply K into Q1 Q2 divided by R square. We normally have the habit of just putting the values and take out the calculator and do it. Let us try to do slightly more justice to such problems. So whenever such problems are given, so we first put down the data. So we write F is equal to K is known to us. And one thing we have checked here, all the values are in SI system. Charge is in Coulomb. Sometimes it may be given in microcoulombs or in some other units. You convert them into Coulomb. The distance is given as meter. It may be given in centimeter or some other value. Convert it into meter. And of course, the K is in SI system. So all the data are in the SI system. So I put an exclamation mark here. This is the area where the students make majority of the mistakes by choosing the wrong unit. So you choose the unit correctly and put the data. So it is 9 into 10 to the power 9. Then Q1 is 3 into 10 to the power minus 6. Q2 is minus 1.4 into 10 to the power minus 6 divided by 0.14 square. Now here we can show, of course, the detailed calculations, but you can do one thing. You can group the powers of 10 on one side and all the data onto the other side. Like if I do just one step, just to show you, if I do one step, so F will be, we can simply write 9 into 3, if we take the minus sign here, into, we write it here 14 because we'll adjust one power there. So we'll reduce one power from here, it will be 8. So 6 and 6 minus 12 and 8. So it will be into 10 to the power minus 4. And in the denominator, it will be 14 into 10 to the power minus 4. So data is such that this 14 and 10 to the power minus 4, 14 and 10 to the power minus 4 get cancelled. So it is minus 27 by 14. And if we calculate, it will be coming out to be 1.93 Newton approximately. It will come out to be 1.93 Newton approximately. So we can work on a little bit with the numbers to make it comfortable so that our calculation time using the calculator also reduces. So this is a very, very important step. This problem is very simple, but I wanted to show you the step the stages involved, and how you should be careful about at each and every stage so that you come up with the correct answer. Now let us move to the next problem. This problem is a slightly different, it's more on a logical sense. So describe the changes in the magnitude and direction of the force acting on one of the charges in an electric dipole when the distance between them increases. Here is a new word you are finding, electric dipole. I hope all of you know it, but let us still discuss briefly. So two charges. Okay, so we have two charges. So maybe one is plus q, another is minus q, and they are separated by a distance r. Such an arrangement constitutes an electric dipole. Such an arrangement constitutes an electric dipole. And most important part is such dipoles, you have studied a lot in chemistry when we talk about the molecules, their structure, their orientation, it comes time and again there. So it is told that their distance is increasing. So the value of R is increasing. So what will be the change in the magnitude and direction of the force? First of all, they are moving in the same line. We assume that their distance increases, so they are moving in the same line. So the first thing, if they are moving in the same line, so number one point is the direction of force that remains unchanged. The direction that remains unchanged. It will not change because the direction is actually acting along the line. And number two, when we talk of the magnitude, when we talk of the magnitude of the force, the important part is that this magnitude follows this Coulomb's law. So force, as we all know, it is K into Q1, Q2 by R square. So as it is like this, so what happens, the distance is increasing. So if the value of R increases, we know this value force is inversely proportional. So value of force is supposed to decrease. So if the value of R is seen to increase, the value of force is going to decrease. And it's quite logical, as they are moving apart, the distance increases, so the force of attraction between them reduces. So the magnitude remains, it does not remain unchanged, magnitude gets changed. So the magnitude reduces. As the distance is increased, the magnitude reduces. So you can encounter such problems also where you need not really do some physical calculations, but you have to apply some logic, and that is only possible if the basic understanding about the theoretical aspect and the formula, the rules, the laws, that are clear. So I hope you have understood this. You please share your comments in the comment box. If there are any difficulties, any doubts that you have, and if any changes that you want in such videos. And with this, I come to an end of today's video. We'll continue with the next video. In that, we'll discuss the effect of multiple charges on a single charge. So that's the principle of superposition. Till then, have a great time ahead. Thank you.